fall break that there was a new university rule that you're not allowed to do any schoolwork over fall break, and therefore none of you studied for the exam tonight, probably, right?
Why did you schedule it today?
I knew the rule was coming, and as a conscientious objector, I decided to schedule the exam immediately after fall break. Are there any questions about logistics in the class, the exam tonight, things like that?
What room?
I think it's the same room. Is that correct?
Yes.
155 Olin. Any other questions? Were you guys all crammed into that little room because you didn't have a key to a bigger room? Was that the problem? On the review on Sunday night? Luke?
Yeah, no, we just debated. I debated.
You just thought it would be fun. It'd be fun to be crammed in there. Okay.
There's more blackboard seats.
So today we're going to go on with rigid object rotation. I decided this semester to make the exams material safely way before the actual lecture material. So you have the homework, you have the solutions, and so on. So this is skipping ahead almost 2 weeks from where you were if you have your head buried in the exam tonight. So you have to jump ahead a little bit, and I'll review a little bit of what we were doing. The main formula for kinematics, the geometry of motion, that we're going to deal with for the rest of the semester, or at least one of the main formulas is this. It's a kinematic formula. It's about geometry, and I will show you some examples of this formula. What's the idea of this kinematics is that in mechanics, we want to pay attention to mass times acceleration and things related to mass times acceleration. We have to calculate the acceleration. When objects are rotating, it constrains how the parts can move relative to each other. And this is the key formula for figuring out how the parts move relative to each other in rigid objects. Let me just give you some intuition for the main idea here. And I need some rigid object besides, say, my computer. Is that if you take any rigid object and move it around in crazy ways, if you fix your attention on one point on that object, so you just fix your attention on that dot, then if you look at some other dot, so you're fixing your attention on this dot, and you're also looking at this dot, what you see is that all this dot can do relative to this one is go in circles. So whatever complicated motion this thing has, this dot is going in circles around this one. And that's true for this one relative to this one. If you fix your attention on this dot, what you see when I do this is this motion. And that's true for any pair of dots. And so in 2 dimensions, for any 2 dots, any 2 points on a rigid object, all they can do is go in circles around each other. And so circular motion then becomes central because for rigid objects, all motion in some sense is circular motion, where you're looking at one point relative to another point. And that's the key idea we're going to get to. Okay, so let's look at some rigid object. Classically, objects in mechanics are called bodies. I don't like to call them bodies because I'm in the subject of mechanics. And for example, an arm is a body, and a finger is a body, and a leg is a body. It's easier to call them objects. But traditionally, they're called bodies, so you use the script letter B. This is a script, capital B, which means body. Here's some body. This is a rigid body, or a rigid object, means the parts don't distort relative to each other. Any line segments you draw stay fixed in length. Any angles you draw stay fixed in magnitude. And what we're going to do is look at some vector which we draw on this object. Now, a key vector that we would draw would be the position vector of 2 points, and I'll show you that in a minute. But let's just say we just draw some vector, and it could represent anything. Then we want to know what's the rate of change of that vector. Well, in a little bit of time, what happens is this vector rotates a little bit. How much does it rotate? It rotates by the angular velocity times a little bit of time. How much does this q vector change? It changes by delta q, or delta q divided by delta t. And so what's the rate of change of this vector? Is this vector itself multiplied by the rate of rotation in this perpendicular direction. Now, how can you represent that in one tidy formula is with this formula, which is called, the Qdot formula. I guess I shouldn't apologize to you for knocking my own glasses off. Okay, so here's the Qdot formula. So what are some key examples of this formula? If we draw some object here, and we have some fixed coordinate system I and j, and some rotating coordinate system I prime and j prime, these things are going to rotate with the object. Therefore, they follow the same rules. So the rate of change of I prime is omega cross I prime. And it's a funny kind of cross product here because we're doing two-dimensional problems and the omega is sticking out of the board. So we use three-dimensional vectors to do two-dimensional mechanics. And why do we use it? Is because this omega cross takes us from the k direction, sticking out of the blackboard, back into the blackboard. So if we take omega crossed with any vector in the plane, it gives us another vector in the plane orthogonal to that vector, which is just the direction we want. And therefore, j prime dot is omega cross j prime. So those are some key examples. Another key example is, let's look at the velocity of point B relative to point A. What do we mean by that is we mean the position of B with respect to A dot. What do we mean by that is we mean the position of B minus the position of A relative to some origin dot. And this is then omega cross the position of B with respect to A. So if we draw two dots here, A and B, and this is really the easiest example to think of, the one corresponding to the pad of paper I showed you, the velocity of this point, B, relative to A, is the velocity of something going in circles. It's theta dot times r, tangent to the circle. Theta dot is omega, so it's omega times r, tangent to the circle, but the tangent to the circle direction is in the direction of omega cross r. So if we take omega cross r, it gives us a vector that's in the right direction and with the right magnitude. So if this is the position of B with respect to A, this then, perpendicular to it, is the velocity of B with respect to A. So that is probably the most important application of this formula. Now we want to use this in mechanics. In mechanics, we're interested in acceleration because that's the stuff that shows up in linear momentum balance and angular momentum balance. So what about the acceleration of B with respect to A? And this is a derivation I did in class in a big hurry at the end of class just before break. The acceleration of B with respect to A is the rate of change of the position of the velocity of B with respect to A. So that's equal to what? Well, the velocity of B with respect to A, we said, was the omega cross of the position of B with respect to A. So now we need to take the derivative of that expression. How do we take the derivative of cross products? The derivative of dot products, cross products, and scalar products all follow the product rule of differentiation. So if you go back to your math 191 book and look at the derivation of the product rule, you will see that the derivation works whether you have scalar times scalar, scalar times vector, vector dot product with vector, or vector cross product with vector. The rule of the product rule of differentiation works for all of them. So to do this, we use the product rule of differentiation. So this turns into omega dot cross of r b with respect to A plus omega cross. And now we have to take the derivative of r of b with respect to A. But this is the problem that we just solved. What is the rate of change of position of B with respect to A if B and A are 2 points which are fixed on the object? It's just omega cross B with R of B with respect to A. And then we get to this very intimidating looking formula, which has a cross product of a cross product. So it makes you dizzy. Cross products already make most of us dizzy a little bit, and now we have a cross product of a cross product, which twists your mind around twice over, and it's a scary looking thing. Now for these two-dimensional problems, this scary looking thing isn't so bad. And I'll show you why it's not so bad. Is because if we draw a picture to go along with this, and here we have, let me just pick 2 points here. Here I have A, and here I have B, and here I have R of B with respect to A, and then we had omega sticking out of the blackboard, which was omega K. Omega cross of R of B with respect to A was just in this direction. So that's omega cross R of B with respect to A. So in terms of this picture, we know the direction of this vector. Now we want to take omega cross that, and we can use the right-hand rule. So the right-hand rule says we take the cross product of something sticking out of the board with that vector, and that sticks right back in this direction. So this is omega cross R of B with respect to A. Notice, by the way, that when you have two cross products, you cannot use the associative rule of multiplication. Omega cross of omega cross R is not equal to omega crossed with R. Why not? What would that be if I put the parentheses over here? 0, because anything crossed to itself is 0. So this thing is not 0. It looks quickly like 0 if you assume the associative rule, but the associative rule doesn't hold. Now, when I did the succession of cross products, first omega cross R, and then omega cross R, in each case, the pairs of vectors were orthogonal to each other. So in each case, the magnitude was equal to the product of the magnitudes. Because when you have perpendicular vectors, the cross product, remember, is AB times the sine of the angle between. When they're perpendicular, the sine of the angle is 1. So the magnitude of this vector is just the magnitude of this times the magnitude of this times the magnitude of this. And the direction of it is in the minus R direction. So this then turns into, the first term is omega dot cross of R B with respect to A. And the second term has magnitude of omega squared times the magnitude of R B with respect to A, but its direction is then the acceleration of B with respect to A. And this is the same derivation I did at the end of class just before break. Now there are two ways to, not two ways, there's another way to think about this term as a sum of two terms. What we get here is, this is like the term you had from circular motion, theta double dot times R, which is that there's an acceleration tangent to the circle, or if you think of this point as going in circles around this one, there's an acceleration tangent to the circle. So this is acceleration tangent to the circle. And then there's a centripetal acceleration, which is a minus theta dot squared times R. And this is a centripetal acceleration. Okay, so this then relates back to stuff which is you studied for the exam. What's the connection here is that if all we're looking at is this one point, we could keep track of this one point with a polar coordinate and the angle this point makes relative to this one. If that's all we were doing, we could just use the polar coordinate formulas, and this is the answer for these polar coordinate formulas. The reason we don't use those polar coordinate formulas now is that they work for this pair of points A and B, but for another pair of points A and C, or C and D, each different pair of points would have a different angle. And the formula would be correct, but we'd have to invent a different angle for every pair of points. The benefit of this formula here is that it works without any explicit reference of angle at all. It just has to do with the relative position of the 2 points. The angle gets hidden inside the position vector. Okay, so let's let you stare at this for a minute, and then ask me questions if you like. Or ask me to repeat any part of it.
So is there a coordinate system which is in the cross product line, second from the bottom?
Is there a coordinate system implicit in this expression? And the answer is no. This is a coordinate-free representation. I would say the answer is no. Now maybe you would say the answer is yes. We can always be keeping track of relative to some fixed coordinate. We have a fixed coordinate system, so whenever we say acceleration or velocity, we're always talking about relative to some fixed coordinate system. And then do we need some rotating coordinate system? And in a way, the beauty of this formula is that it works without actually mentioning any explicit rotating coordinate system, as opposed to the polar coordinate formula where you have to have an explicit rotating coordinate system. Is that it? Is that what you wanted me to say? Okay. My straight man. Any other questions? Now, if you get a little dizzy when you see this, join the club. Everybody does. 2 dimensions, fortunately, this collapses to this. And all you have to do is remember the reasoning from how you get from here to here. In 3 dimensions, this really is a screwy term, but we are not going to do much 3-dimensional mechanics in this class, so you're not going to have to deal with that in this class. You should be aware of the fact that in 3 dimensions, this term does not simplify in this way. We're just not going to use that here. Yes?
Can I ask a question about an example?
Yes?
Is the omega defined relative to the coordinates that you define your I prime? Because I prime, J prime aren't really rotating. They're rotating relative to I and J.
Right. I prime and J prime are rotating relative to I and J. And so what do we mean by omega, or what do we mean by theta? What's the question?
So the omega is relative to the coordinates.
So the omega is, this is probably the key formula in terms of what omega is. It's the rate of rotation of any angle, any line that you mark on the object. So I could mark over here a theta 1. I can mark over here a theta 2. I can mark over here a theta 3. I could mark another line over here, and relative to the horizontal, I could call that theta 4. I could mark another line over here, and I could measure its angle relative to any fixed line, and call that theta 5. And the claim is that the rate of change of all of these angles is the same as each other, and that's the definition of omega. Pick any line segment on the object, look at how much its angle relative to any fixed line in space, look at how fast that angle changes, and that's the definition of omega. Does that address your question or no? Okay, so let me just jump to a mechanics example. And this is, I'm going to give you, if time allows, I'm going to give you a quiz on this example. So today's quiz is going to be on this example. So if you follow it carefully, you will get the quiz question right. And if you don't follow carefully and ask a lot of questions, I won't get to the quiz question. Okay, so what we're going to look at is a pendulum again. And now we're going to take a pendulum, which is some kind of crazy object which is hinged at some point. Let's call that hinge point O. The pendulum has some center of mass G. Let's just use as our reference point on this pendulum the angle that this point G makes. So let me call that theta. Let's keep a track of a length here, which is the distance from the origin to the center of mass. If we need it, we can put a coordinate system here, I prime and J prime. And these are coordinates that, in this picture, they look fixed, but as this object rotates, they rotate with the coordinate, just like polar coordinates rotate with the particle as the particle moves around. Just to keep things nice so that we can have cosine theta and sine theta corresponding to x and y components, we'll pick a fixed coordinate system with x down and y to the right. We don't have to do that. It just makes it so that if and when there are polar coordinate formulas, they will have a familiar form and you don't have to work them out from scratch. Okay, we've got this pendulum. It looks like the pendulum that Pranav did 5 different ways, and I did 1 or 2 different ways. But it's different. The difference is that this is not a point mass pendulum. It's a rigid object, and it swings, and we have to worry about the fact that there's mass not just in one point, but there's mass in a variety of points. So we could draw the center of mass of this thing here, and we can put the hinge here, and we can look at this thing swinging, and it looks like it swings like a pendulum, but the rate at which it swings, the frequency, might not be given by making the assumption that all the mass is in the middle here. In fact, it's not given by that, and we would like to figure out what is the frequency of this oscillation, taking into account that there's mass all over the place. Okay, so how are we going to work this out? If you do any reasoning involving the laws of mechanics as opposed to just kinematics, so if you use so-called force balance or linear momentum balance or moment balance or angular momentum balance, you have to draw a free body diagram. So we draw a free body diagram, we draw a picture of the system of interest, we cut it free from the universe. In this case, we're cutting it free 2 different places. We're cutting it free from the hinge, and we're cutting it free from the world. In cutting it free from the world, we have to fool it into thinking the world is there, and we do that by putting a gravity force, which is the total mass times g. Then we cut it free from the hinge. Just to avoid sign problems in my algebra, I'm going to call this Rx, and I'm going to call this Ry. I can call them whatever I want, but it's not have a reaction in the x direction, 1b is positively to forces in the x direction. And then here we have this point g, and then we say, what are the basic equations of the system? So we have the linear momentum balance equation, and linear momentum balance says on this system, the sum of all the external forces is the total mass times the acceleration of the center of mass. Always we mean the external forces. There's zillions of internal forces here because this is made of all kinds of atoms that are interacting. Don't include the internal forces in the linear momentum balance equation. Or we make the assumption, which is accurate to at least as accurate as anything you'll live with in your life, that all the internal forces cancel. That you can think of them as coming in action-reaction pairs. That's not really an accurate representation when you get down to quantum mechanics. But whatever they are, they cancel. Okay, so what does linear momentum balance say in this problem? It says that Rxi plus Ryj, and by drawing them the way I did, I get the benefit of just having positive signs over here, plus Mgi, it looks funny that I'm calling it positive I, but that's the sign convention I picked, is the mass total times the acceleration of the center of mass. Now, I'm not going to figure out the equations of motion from this equation. Why not? Well, how many equations do I have here? Basically 2 scalar equations, because it's a vector equation in 2 dimensions. How many unknowns do I have here? Well, I have this is an unknown, this is an unknown, and this, how many unknowns are hidden in here? Well, if I do my kinematics correctly, the only unknown in here is going to be theta double dot. Well, that's not even true. Theta dot is going to be, so we're going to have theta dot, theta double dot. We have lots of unknowns here. Okay, so let's work out what this thing is here. This acceleration of g is equal to, and now we get to plug in our formulas. It's omega dot cross the position of g with respect to O plus or minus omega squared the position of g with respect to O. And what do we mean by omega? Omega is this theta dot. So if we make that substitution in here, here we have a theta dot, and here we have a theta double dot times k. This thing we think of as known. This thing we think of as known, 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 and unknown. So this is 2 equations and 4 unknowns. So we're not going to be able to solve this. We're not going to be able to get the equations of motion from this linear momentum balance equation or from any linear momentum balance equation. Okay, any questions about this so far? So we'd like the equations of motion. What do we mean? We'd like to know, we'd like a crystal ball, we'd like equations that tell us how to predict the future. We'd like something that tells us what theta double dot is. If we knew theta dot, which we always pretend we do know when we're writing equations of motion, because at any instant in time, the state is given by the position and velocities. So if we knew theta dot, and we knew those reaction forces, we'd have the equations of motion, but we don't have the reaction forces, and we don't have any way of finding them yet. Okay, so what are we going to do to get the equations of motion? We can use angular momentum balance, which is our best friend in statics and mechanics, because it's the tool that lets us solve most problems most easily. And this is that the sum of moments relative to O is equal to the rate of change of angular momentum relative to O. So in advanced mechanics, in dynamics, this is the most important term characterizing motion. It's the rate of change of angular momentum relative to some point. Okay, so on the left-hand side, we have the position of G with respect to O, crossed with the gravity vector, which is mgi. That's just left over from statics. The left-hand side is always evaluated in dynamics exactly as it is in statics. This is left-hand side of linear momentum and angular momentum, not left-hand side of the differential equations. Okay, now the right-hand side we have to work out. Now we have this system with distributed mass. We have to add up over the whole object, so over all the mass, what is the contribution to this angular momentum. If you just had one bit of mass, we would look at the acceleration of that bit of mass. But we don't have one bit of mass. We have lots of bits of mass, and we have to add up over all the bits of mass. So rate of change of angular momentum for one particle is r cross ma. For a collection of particles, is add up r cross ma for all the particles. And for a continuum, that's the Riemann sum written in integral form. You take r cross a dm, where all the different points have different position vectors. They have bits of mass, and they all have different accelerations. So now we need to work out what is this acceleration, and we get to use our kinematic formula. So it's given by omega dot cross the position minus omega squared times the position. Any questions so far? Okay, what's our goal again? Our goal is we want to find a differential equation to figure out how this thing moves. We'd like, given this position and velocity, to figure out what is theta double dot. What are our tools? Our tools are the laws of mechanics, most importantly linear momentum balance and angular momentum balance. Most practically, most often angular momentum balance. Angular momentum balance says the torques on a system relative to a point are the rate of change of some kind of rotation thing. The fundamental definition in mechanics is this h dot. It looks like the time derivative of something, but actually it's best to think of this as a quantity in itself, which happens to integrate to be something else. This is the fundamental quantity. Think of it as a symbol that happens to have a dot on top. It happens to be the time derivative of something, but that's actually not the most direct way to calculate with it. The most direct way to calculate with it is to think of it as r cross a added up over all the particles. Now we're going to do this addition over all the particles, but all the particles have different positions and different accelerations, so we have this whole complicated expression. So, on the left-hand side, we have this cross product. This one's easy. It's a 2D cross product. All the coordinates are lined up right. We don't have to write this out in x and y coordinates and use determinants and stuff like that. We can just look at the distances. That mg force has a lever arm of what? L sine theta. And then we look at the cross product, r cross mg. It points in the minus k direction. So this is minus L mg sine theta. k. If you want to write out all the components and write the determinants, you can, but that would be the long way to do this problem. That's on the left-hand side. On the right-hand side, we have to substitute this stuff back in. We're doing the integral over all the mass. And now we have the position relative to O crossed with, and now we have a sum of two terms. One is omega dot crossed the position with respect to O, and the other is minus omega squared R with respect to O. Looking at every little bit of mass over here, we're adding up over all these bits of mass. Each of them has some acceleration. One part of it is orthogonal to the line from the origin, and one part is directed back towards the origin. The orthogonal part is like a theta double dot times r. In this case, we write it as omega dot cross r. And this one is like minus theta dot squared times r, and we write that one with this minus omega squared times r. Now we're going to take the cross product of that acceleration, multiplied by mass, with this position vector. What happens when I take the cross product of this vector with that vector? I get 0. So here we have an r cross r gives 0. So this term drops out. So then this just turns into an integral of r with respect to O cross omega cross r with respect to O. And then we add up like this, and there's a dot on that thing. Now again, we get dizzy, cross products of cross products. But again, we're lucky that this is a two-dimensional problem, and all of these vectors, every cross product is between vectors which are orthogonal to each other. So we can do this in our heads without writing out all the components. Now if you want to write all the components, you can do that, and you'll get the answer that we're going to get here. What is that answer? If we're looking at some O here, we're looking at some R with respect to O. And first we take omega dot cross that R with respect to O. That's a vector pointed in this direction. Omega dot cross R with respect to O. That's the tangential acceleration. That's the theta double dot times R. That's thinking of the car going in circles, and the foot's on the gas. It's going faster and faster around the circles. It's got an acceleration tangent to the circle. It's not the centripetal part. It's the part having to do with rate of change of speed of this circular motion of this point relative to this one. Then we're going to take an r cross that. R cross that sticks right out in the k direction. All of the vectors are perpendicular to each other, so all of the signs between the vectors and working out the cross products are 1. So this whole thing then turns into the integral of r with respect to O, the magnitude of that squared times omega dot times k dm. With a hat on it. Okay, so that dizzy cross product doesn't turn out to be so bad for these two-dimensional problems. Now, can we pull something out of the integral? We're looking at all different points and all different masses, so we can't pull the r's and the m's out of the integral. But for this one rigid object, certainly the k vector is constant. We can pull that out of the integral. And all the different points in the object are rotating at the same rate. They all have the same omega. That's why we have this concept of this omega, this key concept of this omega over here. Go back to blackboard number 1. Omega is the angular velocity. So we can talk about this as the angular velocity. Why is it the? For one rigid object, there is only one such thing. So this then turns into omega dot k times the integral of the position with respect to O squared dm. Now this quantity shows up so often that we define it like this, and we call this the moment of inertia. And this is called the polar moment of inertia. in three-dimensional mechanics, we have other moments of inertia to deal with, but for the gyroscopic lab, we're not going to deal with those other moments of inertia in this class. I don't think. Okay, so we have this definition of this quantity, and that takes us then all the way over to what we want to get to. We have minus LmG sine theta k is equal to, and then on the right-hand side here, we have omega dot k times this I0. And we can take this and dot both sides with k, and then we can get theta double dot. Why theta double dot? Because omega dot, theta double dot, is equal to Lmg sine theta divided by I0. So that's our pendulum equation. We've got our differential equation. What does it look like? It looks just like the differential equation we had before. Let me write it, this grouping terms together. We have here minus Lmg over I0. It looks just like the pendulum equation for a point mass. But instead of just a simple L over G, we've got this complicated expression. Let's do a special case, just to check that we did everything right. Let's do a point mass. So the point mass, we'll have an M here, we'll have an L. What is, for point mass, what is I0? It is just ml squared, because when we add up over the mass, the distance squared, it's just the mass times the distance squared. So in that case, the pendulum equation turns into theta double dot equals minus Lmg divided by ml squared times sine theta, which then gives us the theta double dot is equal to G over L sine theta, as we had before. It agrees with what we had derived 5 different ways. But in general, this is not what we get. In general, we get a more complicated expression. Now, what is that more complicated expression? If we use the parallel axis theorem, the parallel axis theorem tells us that I0 is equal to Ig plus ml squared. And where do you get that from? You can read the moment of inertia section of our textbook, or you can read the moment of inertia section of your math textbook, or you can read the moment of inertia section of your physics textbook. All of them will have a derivation of this parallel axis theorem. Yes?
Where it says that theta double dot equals negative Lmg over I, where does that other negative sign come from?
Is this an honest question or a dishonest question?
I'm not sure.
I would call it a dishonest question. Came from the depths of the crossed neurons in my confused brain.
That's where it came from.
Yes?
So before, especially when we did the car problems, we didn't do the R cross ADM. We just did R cross the center of mass.
That's correct. That's correct.
Does that yield the same thing?
No. So in the car problems, where we have this translation, rate of change of angular momentum we can think of as a sum of two parts. So the most general case, where an object is moving in general ways, which we haven't got to yet, is that the rate of change of angular momentum is one part associated with the center of mass motion and one part with rotation about the center of mass. Since the car has no rotation, all we look at is the motion relative to the center of mass. Okay. So in the car problem, the moment inertia doesn't show up because we have no rotation.
So from this, why isn't there a R cross
Why don't you hold on to that for a minute, and I'll do a full answer to that question. So this is the general case. So that means that again we can write our pendulum equation yet a different way. To LmG divided by Ig plus ml squared. And then we have our sine theta. So if we have a point mass, we get rid of this I relative to G because there's no moment inertia relative to the center mass, and the equation reduces to the particle equation. Okay, think about life, and then ask me a question. I'm going to spend a full minute or so erasing blackboards here. I think I'll leave that last one because it has the problem statement on it. Okay, any other questions before I go on? Yes?
Generally, summing up over small pieces of mass is kind of tricky.
Yes?
Are we going to end up using the parallaxis theorem in almost all cases?
No. You're going to do something different still, which is in answer to the question that the green shirt guy asked. Okay, the question is, are we going to use the parallel axis theorem in all cases? And I'll tell you why not, just quickly. The reason why not is that this problem is one special problem, where you have circular motion about an origin. In general, we're going to be interested in more general motion, and this formula with the I0 is only relevant when you have motion about a fixed point at 0. So that formula is only useful for pendulum problems. Now, it turns out that those are the only problems you did, so it looked like that was the general formula and you used the parallel axis theorem. And now we're doing more complicated mechanics, and that particular formula is not that useful. Okay, so I will get to that in a minute. Okay, let's just do a sub-example. A sub-example is, say, take this thing, and let's take a uniform stick here. And the uniform stick has length L, and here is G, and G is down here a distance L over 2, and this thing has some mass. And for this problem, we have that I0 is equal to Ig plus ml squared. But L is L over 2. Ig is this 1/12 ml squared plus, here we have ml squared. Sorry, this is 1/3 ml squared. But what do we have here? We have that L, the distance that was relevant here was capital L divided by 2. So this turns into 1/12 of ml squared plus ml squared over 4, which turns into I0 equals ml squared divided by 3. What does that do to our pendulum equation? It turns it into theta double dot is equal to minus 3g over 2L sine theta. And you compare this with the point mass. And in the point mass, we had theta double dot equals minus g over L sine theta. So what we see is that this pendulum is slower in some sense by 50%. Now when it comes down to looking at the frequency of oscillation, it's only slower by about 22% or something like that, because there's a square root. A key moral to pull out of this comparison is that when you have a rigid object and you have a motion of the object relative to some point, and you have a rotation, that the motion relative to this little correction, you think of it as a correction in the parallel axis theorem, is bigger than the moment of inertia term. So the resistance of this whole thing to rotation, the inertial resistance, is dominated by the center of mass motion, not by the rotation about the center of mass. And that, I'd say, most often works out to be the case. What's the general case we're going to work on, the general 2D case, just to answer the question that was asked now twice over, is that we have, we're going to write this as the position of the center of mass relative to O across the mass times the acceleration of the center of mass plus Ig omega dot k. For the pendulum, this becomes equal to I0 omega dot k. So here's the case that I derived for you today. The more general formula is this one. These two give the same answer, and we can work out that algebra if you like, but I don't have time for it now, so you can do it yourself. So you can do this calculation and see that this answer gives the same equation. I recommend that you do that calculation as using angular momentum balance and using the polar moment of inertia about O. But since this is a general formula, this is the one I recommend you use more. In car problems, this one drops out. In problems where you rotate about the center of mass, this one drops out. And in general, you have both of these, which happen to reduce to this if point O is a fixed point of rotation. So does that address your two questions, red shirt, green shirt, guys? Both of you happy with that? Okay, so now let me give you a puzzle problem, which was given to me at a conference. So I was at a biomechanics conference, and somebody was working on the mechanics of legs, and they had this problem of, they were looking at the swinging of a lower leg like this, and they were trying to invent prosthetic devices and do experiments, and they were really trying to do this. And somebody did experiments where they clamped weights onto the leg to see the effects of the mechanics, and they did it wrong. And so somebody gave this puzzle problem to the audience to show that people didn't have this stuff right. And the puzzle problem was, take this stick and look at how fast it swings. That's the lower leg. Now clamp on a extra mass at the center of mass and see how fast that swings. So right there at the center of mass, add an extra mass. And we'll call this B and we'll call this A. And the question is, for your quiz now, is B faster than A? Slower? Same? Can't be determined? I have no idea. So here's today's quiz. You can answer, if you followed carefully what I did today, you can answer this quiz question from what you have seen. So think about it for 1 minute and vote. Let's see, I'll hide your votes from each other so you aren't copying each other. And then, so is the question clear? It's meant to be a biomechanics experiment. We take legs like this. We look at how fast they swing. We clamp an extra weight on the center of mass and see if it swings faster or slower, or stays the same. Okay, 10 seconds left. Ready? Let's see, I should lock up the vote so you can't change your vote. Locked up, I think. Here's your vote. B is faster, is slower, it's the same, can't be determined. Well, you voted the way that the vast majority of the people in the audience that day voted, which is why the guy gave the talk, because he knew that people got it wrong. The right answer is A. So how many of you did I get? Okay, so one thing is you know enough to do the calculation. So those of you who didn't get it right, do the calculation. Let me just tell you intuitively how to get the right answer without doing any calculations, which is if you look at this one versus this one with nothing but a point mass exactly here, I just showed you that this one swings slower than this one. That's the whole calculation I just did over there. So this one swings slower than this one. Why? It's got the same gravity force driving it, but it's got more inertial resistance. It's got the resistance from the point mass plus the resistance to rotation. So this is faster than this. If I glue these together, this one is trying to drag this one along all the time, so it speeds it up. And this is the two glued together, so this goes faster. If you don't like that intuitive explanation, do the arithmetic and you'll see that it works out like that.